Hi everyone, my name is Pingfu Chao. Today I'm going to present our paper, a survey on map matching algorithms. Survey paper, I will first introduce the map matching problem and its formal definition. Then I will summarize previous surveys and explain why we need a new survey on this topic. Regarding our proposal, we propose a new way of categorizing existing map matching solutions and discuss the main challenges in this field through experiments. Finally, the conclusions are listed in the end. So nowadays, the GPS-equipped devices are used everywhere. People use those GPS devices to identify their locations all the time, which is called GPS positioning. Such technique is widely used in navigation, vehicle tracking, traffic analysis, and so on. However, most of you may encounter such case where the navigation tools recognize you as driving on the right road, as shown in the example here, and ask you to turn right, but you are actually on the left road. Such issue is caused by a GPS error. In fact, GPS data are always inaccurate, which is why we need map matching to correct those GPS errors. To formally define the problem, we first introduce several data sets. So a trajectory is a sequence of spatial temporal samples, each of which contains coordinates and a timestamp. Those samples are obtained from positioning systems like GPS, Bluetooth, and Wi-Fi. The major difference between those data sources is their data quality, which is measured by the measurement errors and sampling errors. As shown in the example, we can clearly see the green trajectory is much different from the blue line, which is object's actual driving routes. The two data types are the road network graph and the route. Therefore, given a trajectory and the underlying road network, the map matching problem tries to find the actual travel route of the given trajectory, like in the right example. The black line is the map matching result of the red trajectory. In fact, map matching is not an easy task. More than 100 papers has been proposed solving the map matching problem in the last 2 decades. Different solutions work for different levels of trajectory quality and working scenarios. In general, data with lower sampling rate and accuracy are harder to be matched. And regarding the working scenarios, there are online map matching and offline map matching. So online map matching usually used in navigation system, and every time it only matches the current point of trajectory, and because the points are given sequentially, so you don't know the subsequent points, you only know a few preceding points. So in that case, if you are in front of a fork like this, you don't know which direction the object will take, so there might be some matching issues. But for offline map matching, because the entire trajectory is given beforehand, so you know the subsequent points, so you can always guarantee a continuity of your matching results. And in that case, offline matching is usually aimed for the optimal performance, while the online map matching aims for the interactive processing speed. According to our study, we found that there is a lack of survey in this field. The last comprehensive survey was done in 2007, which means most of the recent solutions are not included. Moreover, we find that the categorization proposed in that survey is no longer feasible, because if we consider the recent solutions, they will all fall into the advanced category, which doesn't make any sense. There are a few recent surveys proposed, but they only focus on certain aspects, like the online map matching surveys proposed in 2014 and another application-based surveys proposed in 2018. We also realized that the recent work do not receive enough attention simply because their performance didn't improve significantly over the previous solutions. It is because the current way of evaluation is not designed properly, and most of the map matching solution perform similarly under the current evaluation process, which is not a good choice. Therefore, in our work, we first conduct a comprehensive survey on map matching problem. We propose that the map matching solution can be decomposed into a map matching model and a set of tuning techniques. So for map matching model, we propose a new way of categorization, which consists of 4 different categories, including similarity model, state transition model, candidate evolving model, and scoring model. In addition to that, we try to identify the challenges remain in the current map matching problem. So we find new factors that affecting the map matching qualities and also the current map matching issues. So first, I will introduce our new way of categorization. So the first category is called similarity model, which can be further divided into distance-based model and pattern-based model. So the idea of distance-based model is to try to find a sequence of rows that is closest to the trajectory. So the solutions in this category have different way of defining the closeness. So one of the typical solutions use the French distance to measure the closeness. Because French distance is decided by the largest distance between these two sequences, so it's really sensitive to outliers, and also because the calculation of French distance is really time consuming, so it's really slow. Another pattern-based solution, the main idea is try to find a similar travel pattern in history so as to use the historic map matching result as the result for the new trajectory. So in this category, so if trajectory first will be segmented into multiple OD pairs, and for each OD pairs, you try to find the historical map matching result, and then they can concatenate all the map matching result into the final matching result. So this category is good for solving the low sampling rate data because they only need the OD pair information, but it relies on abundant historical data. The second category is called state transition model, which consists of 2 notions, the state and the transition. A state is a set of possible candidates for a trajectory point. For example here, the CI1 and CI2 are 2 candidates for trajectory point PI. So each candidate consists of a probability, which means how likely this candidate is the actual location of that trajectory point. And the transition is each pair of candidates between 2 states have a transition probability, which means how likely the point it transits from the first candidate to the second. It is usually defined by the shortest distance between these 2 candidates. So after using the transitions to connect different states, the whole process became a chain. So the optimal goal for this state transition model is to find a sequence of candidates that with the highest possibility, and this sequence becomes the final map matching results. Actually, many popular map matching solutions fall into this category, like the HMM model and the weighted graph techniques. The advantage of this model is that they work in both online and offline scenarios because they can perform quickly and they have really high accuracy. And also by defining the transition probability and the state probability, you can work for various kind of scenarios. However, in online environment, the state transition model have a latency issue because for every the matching of the current stage always rely on a few subsequent states, so you have to wait for a few subsequent points so as to match the current point, which is the reason for latency. The third category is called candidate evolving model, which is quite similar to the state transition model, but it only generates candidates for the first trajectory point, which is called initial candidates. Then for each stage, it only propagate, it try to evolve the candidates and estimate the next location of the trajectory points. And those estimations that are no longer relevant will be removed. And finally, in the last stage, the estimation that have the highest probability will be remain as the final map matching result. So the candidate evolving model can better handle the sudden outliers because you don't need to worry about the candidates of that outlier and its connection to the nearby candidates. But because the propagation through the network is really time consuming, so the candidate evolving model really runs slowly. So the last model is called scoring model, which define a global scoring function and use this function to decide which candidate is the best candidate for every trajectory point. So in this case, actually, the calculation of scoring function is really quick, so it runs really fast. And also it can include different trajectory and road features in the scoring function. However, it is really sensitive to noise. In our experiment, the main goal of our experiment is to identify the influential factor to map matching performance and also the remaining challenges. Therefore, we use multiple datasets for experiments, including a global dataset, which is a public dataset for map matching evaluation, and also our Beijing dataset, which is a private commercial dataset. In addition, we extract multiple sub-datasets from the Beijing dataset so as to simulate different working scenarios with different trajectory sampling rate, trajectory accuracy, map density, and map size. Here, the map density is a new factor proposed by ourselves, which is defined by the density of the rows within a unit of map size. So in our experiments, we identify 3 different data quality challenges. The first one is unnecessary detours, which happens when the sampling rate of the trajectory is really high and also the accuracy of the trajectory is low. In this case, as shown in the red polyline, so the subsequent point sometimes located ahead of its preceding points. So in that case, when we match this kind of trajectory, there will be a back trace, which can be achieved by several U-turns or making a large circle like the left blue line. So in this case, because of the high sampling rate, the trajectory matching result actually deteriorate. So through our experiment, we identify that if your data accuracy is not very high, it's better to have a lower sampling rate data rather than extremely high sampling rate data. To achieve this, we can use a downsample strategy. The second challenge is called matching break. As shown in the right top figure, the green circle region, actually the matching results are disconnected. It is mainly because of the outliers. In matching, the outliers usually are really far from the original position, so its candidates sometimes are disconnected to the other candidates nearby. So in this case, the matching result will have some disconnections. To solve this issue, we need to put some efforts on the data preprocessing to reduce the outliers. One solution is use the compression strategy, but in our experiment, we find out that simply using compression strategy brainlessly will not solve the problem, like if we use the Douglas-Baker compression in this case, but actually after using this compression, the map matching result deteriorate as well. The third challenge is called matching uncertainty. It is really determined by the map density issue. As shown in this yellow circle, in a dense map, it is even really hard for human being to match a trajectory to the road, because it's really hard to determine which road it actually traveled. Through our experiment, we find that the map density play a really important role in deciding the map matching performance, as shown in this bottom left figure. The Beijing U and Beijing R are two datasets with the same map size, but Beijing U double the map density of Beijing R. We can clearly see that there is a significantly drop on the map matching performance simply because of the map density. And also, it is the main reason that the global dataset is not a good dataset for performance comparisons, simply because it has a really low map density and also really high trajectory accuracy, which lead to all the map matching solutions have the similar trajectory matching result. In conclusion, in this paper, we conduct a comprehensive survey on the map matching problems, and we identify the main issue of the previous surveys and propose our new categorizations. Through our experiments, identify three different map matching challenges, and also propose a new influential factor, which is the map density. So that's all for. Thank you. In terms of the question and answers, I think of three different questions. The first one is about how accurate of the current map matching algorithm are. Actually, the map matching performance really depends on the data quality, especially the GPS accuracy and the map density. I find that a lot of ancient map matching solutions proposed like early 2000, they claim they have over 95% of accuracy, but actually they only works on really high accuracy GPS data and on a really sparse map. But recently, the popular solution like the HMM and other ST matching, these kind of solutions, they can achieve average over 90% accuracy on regular GPS data and on really dense maps. The second question about how to measure the accuracy. In our paper, we use the accuracy and the F-score as our measurement. The accuracy is defined by the total length of correctly matched rows over the total length of the matched rows. And actually, there are more than 8 different metrics proposed in different papers in the last 10 years. We've done a comparison between those measurements, and we realized that the accuracy and the F-score are one of the best measurements over those measurements. So we use this in our paper. In terms of the potential future directions, currently most papers don't work on developing new map matching models rather than proposing new tuning techniques. They prefer using new technique like machine learning to do the tuning, like using the machine learning to do the parameter tuning for the scoring model. And also they are trying to do the land level map matching, which requires higher higher quality GPS data. And in addition, they trying to fuse more data source to the GPS trajectory to achieve higher map matching quality, like using the camera data, the Bluetooth data, and the Wi-Fi data, so on and so forth. So that's all for my presentation. Thank you.